The objective of this lesson is to solve real-world problems involving exponential growth and decay. Let's start off with an interesting problem. Number 1. Which option would you choose? Option 1. You can receive $1,000 a year for 20 years. Option 2. You receive $1 the first year, $2 the second year, $4 the third year, and so on, doubling the amount you receive each year for 20 years. In Part A, we're asked to write a function for the total amount of money y you have received after x years for each option. So let's look at option 1. It sounds pretty nice. You receive $1,000 a year for 20 years. So how would we write that as a function? Well, y represents the total amount of money, so I'll start with y equals. And there's nothing special happening here. We're just going to get $1,000 each year. So we're simply going to take $1,000 times the number of years, which is represented by the variable x. Hopefully you can see that this option 1, because you're getting the same amount every year, that's an example of a linear relationship. Now, option 2 is not linear because you're not receiving the same amount each year. There's not a constant rate of change. Instead, you start with only $1, and that dollar doubles every year for 20 years. So option 2 is actually an example of an exponential relationship. We've talked about exponential growth and decay in a previous lesson, and in this example, because you are increasing the amount of money you have, this is an example of exponential growth, which can be represented like this. A is the initial or beginning amount, and then the base is going to be bigger than 1 because you take 1 and add on a rate of growth, and then your exponent is x, which represents the time that has passed. Okay, so let's try to write an equation for option 2. We're going to start with y equals. The initial amount is only $1. That doesn't seem very appealing, especially since option 1, you get $1,000 the first year. But let's keep going and see what happens. So now I've got 1 plus the rate of change, and even though it doesn't give you a percentage of a rate of change, you are increasing that dollar by a whole nother dollar the very next year. And you're increasing that $2 the next year by a whole nother $2 the next year. So it's actually increasing by 100% each time. 100% can be written as, if we move our decimal 2 places to the left, it can be written as 1 to the power of x. Now let's clean this up because the 1 as a coefficient in front is not needed, and then the 1 plus 1 inside simplifies to just 2. And that makes sense because notice in our problem we are doubling the amount, hence the value 2 located here. Okay, so now we're going to fill in the table to find the total amount of money you've received after the given number of years. To do that, we're going to put each equation into y equals and look at the table in our calculator to find the amount of money. So the first equation is pretty simple. 1000x means we'll take 1000 times 1 year, 1000 times 2 years, but the first year that they ask for is 5. So after 5 years in option 1, I'll have $5,000. After 10 years, I'll have $10,000. 15 years, of course, I'll have 15,000. And 20 years later, I'll have $20,000. This looks pretty good. Let's look at option number 2. I'm going to change the equation in y equals to 2 to the power of x. and go to the table. So notice I start with $1 and then it doubles each year. So when I get to 5 years, I have $32. That doesn't sound like much money. But let's go to 10 years. After 10 years, I have $1,024. Still not quite as much money as option 1 seems to be. But look at 15 years. I've got 32,768. And even crazier is that at 20 years, notice it goes to scientific notation because it's so big. But if we arrow over, we can see the actual amount is 1,048,576. So if you chose option 2, you would be in the lead by a lot of money. Number 2, a toy is made up of circular rings stacked on a base. The diameter of ring 1 is 85% of the diameter of the base. For ring 2 through ring 5, the diameter of each ring is 85% of the ring directly below it. Part A. If the diameter of the base is 6 inches, write a function that could be used to find D, the diameter in inches of ring R, where R is between 1 and 5. So notice that if we start at the base, which has a diameter of 6 inches, and then we work our way up, each time the rings are getting smaller by 85%. So this is an example of exponential decay. Let's try to write our function. This time they want us to use D to represent the diameter, so I'll start with D equals. The initial value or beginning amount is our base, which has a diameter of 6 inches. Since it's exponential decay, I'm going to start with 1 and subtract. And then the independent variable will be R, where R represents the ring number. So the only thing we have left to fill into our function is the percent at which the ring diameter is decreasing. Now be careful, it tells you that the rings are 85% of the ring below it. So that means they're actually decreasing by 15% in diameter each time. 15% as a decimal is 0.15. So let's clean up our function. We can also write this as D equals 6 times 1 minus 0.15, which is 0.85. All right, part B, what is the diameter of ring 5 rounded to the nearest tenth? There's 2 ways of working this problem. One way is to take our equation and to put it in y equals, using an x for our exponent. And then we can go to our table and find ring 5 where x is 5. Okay, so that's here and we're supposed to round to the nearest tenth. So we would approximate that to be 2.7 inches. Remember, you can also go to your home screen and take that 6 times 0.85, and instead of raising it to a power of x, actually plug in the ring number, which is 5, and you get the same answer. Number 3, for some time now, the population of the United States has been increasing at an average annual rate of 0.96%. In 2013, the population was 316.5 million. In part A, we're asked to write a function to find the population of the United States, y, after x years. So notice because the population is increasing, this is an example of exponential growth. And it's exponential because each year it's increasing by 0.96%. we're going to need to convert 0.96% to a decimal, so let's go ahead and do it now. Notice the decimal is already to the left of my number, but I still have to move it 2 spots to the left, so that's actually 0.0096. Okay, so let's start our function with y equals, where y is the number of people. And we know in 2013, the population was 316.5 million. Because the population's growing, I'll have 1 plus, and x is my exponent, and it's the number of years. Now, I'm going to plug in my rate of growth as a decimal. And then if you prefer, we can rewrite this as y equals 316.5, but let's combine together the 1 and the 0.0096 to just one number. That's 1.0096. So we're asked to predict the population in 2020. Please understand that we started in 2013, and now we want to know 2020. Well, that is 7 years later. So we want to know what is the value when x is 7. Again, 2 ways of doing that. We can go to y equals, type in our 316.5 times 1.0096. And we'll raise it to x. And 7 years later in 2020, it's going to be, if we round to the nearest tenth again, 338.4. But please understand that that is in millions. Part C, when will the population surpass 400 million? Surpass means that it's going to be bigger than 400 million. To answer this question, I need to scroll down so that the y column is larger than 400. We can see that the first time that that happens is in 25 years. And notice that our starting year was 2013. So if we take 2013 and add on 25 years, that would mean the population surpasses 400 million in 2038. Number 4, the starting annual salary for an office worker at a company is $29,000. If the company awards an annual increase of 6.2%, which graph models this situation after the office worker receives X annual increases? So notice we've got a key word in here, increases, and we're increasing by 6.2% each year. So this is an example of exponential growth. Let's try to write an equation and then see if we can match it to a graph. So notice the starting salary is $29,000 and it's exponential growth, so I'll have 1 plus my rate of growth. And notice the rate of growth is 6.2%. which, if I move that decimal 2 places to the left, is 0.062. Okay, so I could write that number here inside as just 1.062. In fact, I'll do that now to clean it up. And I want you to notice that from your answer choices, there's a couple we can eliminate just by looking at our equation. Notice the beginning amount is $29,000. That represents our y-intercept. So notice answer A does have a y-intercept that's pretty close to 29,000, and so does answer B. But notice answer C starts at 5,000. We can eliminate that one. And D also starts at 5,000. and now we have to have a 50-50 chance of getting this right. So to decide how it increases, we can put our function into y equals, and then look at the table to check a couple of points. Okay, so if I go to 1 annual increase, it should be about 30,000. Let's pick an easier point to check. Notice on the graph, this is a pretty good point to check. And notice that's at 3 years. So let's go to 3 annual increases. And our calculator says the salary is around 34,735. I would say that that is pretty close. But if you compare answer B, notice in 3 annual increases, the calculator says that it's supposed to be 34,735, and we are nowhere close over here. So correct answer is A. This concludes our final lesson on exponential growth and decay. Go practice by completing your assignment.